Hi, so this is a talk that I have presented at the Peers Conference this year. The title is Simulating Photosynthetic Energy Transport on a Photonic Trip. I'm Hao Tan from Shanghai Jiao Tong University. Quantum biology is actually a very old topic. It has covered a lot of natural phenomena that actually involve something quantum. For instance, like bird navigation, quantum smell, quantum amplification, and the light harvesting. Especially for light harvesting, with the energy transport of the photosynthetic effect, we observe that the quantum phenomenon exists in the transport. So there is research on the environment-assisted quantum transport showed as ENACT that introduces both the classical random noise and the quantum phenomenon. Typical topics include the FM molecule and the M13 virus. And very good papers published a few years ago on the natural material introduces the quantum stochastic walk model to model the fluorescence as a function of the donor to acceptor ratio. It has a better fit than the classical super Foster series. So to theoretically research the open quantum systems, we usually use the quantum stochastic walks in the Landau-Blada equations, which use an omega to interpolate the ratio between the quantum and the classical random walks. And to solve this actually involves a lot of matrix calculation. And we used a range-quota method and TensorFlow GPU parallel computing to greatly improve the memory and the time cost. So with a normal laptop, we can calculate Landau-Blada equation with up to 10,000 nodes, while for a normal solver without an optimization, it can only solve like 100 and more. And on the other hand, we care to implement the quantum stochastic walk in the real quantum hardware to make the quantum simulation experiment. There have been different physical systems that introduces the quantum stochastic walk. And the key point is to introduce classical noise terms in the quantum systems. And well, our approach is to use the integrated photonic quantum trip. It is to bring what the bulk objects into a more compact integrated trip. And it can do what those bulk optics cannot do with more and precise engineering on the Hamiltonian terms. We use the femtosecond laser writing to make a large-scale, low-loss, three-dimensional photonic lattices. With this, we make a first spatial 2D quantum walks and measure its transport properties. We later set up the photon source, the quantum circuit on chip, and the photon detection systems to make an analog quantum photonic system. Based on this setup, we have published quite a lot of works on the quantum information processing. Back to the quantum stochastic walk, we have done another work that used delta-beta approach to make the quantum stochastic walk and reach the high randomness. So the key point is to make such a Hamiltonians by introducing the random dephasing noise on the diagonal terms of a Hamiltonian called delta-beta dephasing terms, while the couplings between different waveguide is represented by Cij, the coupling coefficient. So following the similar experimental setup, we do the quantum simulation for the photosynthetic work. We know that for FMO molecules, there's a very high energy transport efficiency, even though it is down into the deep sea with very low photon counts, but still it survives very well because of the high energy transport efficiency, right? It has a very good structure with 7 BCHL molecules, and those scaffold of protein serves as an environment that makes some noise. So here we firstly map the 7-side FMO structures with an array of 7 waveguides to map its Hamiltonians. With the black numbers in bold, it's representing the major coupling strengths between the 7 sides. So we have these 7 waveguides representing the 7 sides of the FMO, and the coupling coefficient, which physically decays exponentially with the waveguide spacing, can be deliberately manipulated to make the strength consistent in proportional to the real FMO case. Now we have done this by setting different waveguide spacing Dij. We make those Cij mapping to the FMO. But mapping the off-diagonal terms like Cij is not enough, right? We also map the diagonal part. The diagonal terms representing the site energy. Here, site 3 has the lowest energy and site 6 has the highest. So we make a static detuning of the diagonal terms of the Hamiltonian, which is propagation constant beta, by controlling the laser writing speed and power. Site energy has real physical meaning, and we make it by tuning the laser speed. And that's not enough, right? Because there is some dephasing noise. Dephasing noise here it's represented by random propagation constant detuning, dephasing delta beta terms. And note that the dephasing noise is not pure Gaussian or the random noise. It's called the colored noise. What is colored noise? Well, it means that it's not white noise. It's the power spectral density degenerates, matches that for real FMO. So we make a Fourier transform of the noise, and then we map this pattern of PSD. We notice that for real FMO, it's having the pattern concentrated at a low frequency region, and our setting matches it well. Well, for white noise, then the PSD will be just very much random. And in the meantime, we consider the vibrational assistance. So in the very recent research, the FMO researchers discovered that the electronic coherence, vibronic coherence, and the vibrational coherence are found to live with different coherence times. So our photonic trip corresponds to an evolution time in 10 ps, which goes beyond the above time scale. Still, it is interesting to investigate a vibrational assistant at a very early stage of the evolution. So we set an additional vibration mode by an extra waveguide with a vibrational coherence strength equal to the gap between the 2 lowest eigenstates of the 7-side Hamiltonian. And as shown in this figure, with vibration mode, we can see at the early stage of the propagation, it does help the transport, which is what the vibrational assistance expected. And now we consider the exciton localization issue. We plot the disorders strengths influence on this transport behavior. So we find that when the disorder strengths increase to a very large level, then we find that mostly the site just oscillate with certain sites. And in the meantime, we can manipulate the dephasing strength. So dephasing strength is the random noise strength. So with the random noise strength as well, we can see when it increases, it becomes more localized. So both large detunings of the site energy and that introduces the strong disorders and the large-scale delta beta dephasing noise would enhance the exciton localization. This actually can be explained with the original theory of environment-assisted quantum transport. With the paper published many years ago, they gave this explanations of the intact theory. So they consider as well a pure dephasing in the blood operators, like this. So by destroying the coherence of the beating, dephasing also destroys the localization and allows the exciton to propagate through the system. When the dephasing rate grows larger, transport is suppressed. This can be thought as the watchdog effect. Rapid dephasing at a rate is equivalent to being measured repeatedly in the side bases at the time intervals inverse. So the watchdog effect suppresses the transport away from the initial site. So there's like kind of a trade-off, and there exists a maximal delta beta dephasing strength that can make a optimal transport efficiency. So experimentally, we want to measure such an optimal dephasing strength to observe the intact effect. Experimentally, we prepare samples of different delta beta amplitude. As can be seen here, the transport efficiency is measured by the ratio of those long sync waveguide and over the total light intensities. So light intensity in this long waveguide clearly goes stronger when delta beta amplitude is getting stronger from 0. So it means some noise helps it to hop out, right? But when it goes even up higher, then this original 7th site is also very bright. This means the transport efficiency goes down a bit. So overall we observe such a peak at around 0.5. There is an optimal transport efficiency. So experimentally, we demonstrate the existence of optimal noise strength for energy transport in FMO. Here are some experimental details. And we also numerically test that for different noise types, not only for our colored FMO noise types, we always can expect such a peak of transport efficiency. So for different noise distributions, such an intact effect is a general phenomenon. And our measure can be mapped to even more complexes on trip. For instance, there are many other photosynthetic molecules like PE545, PE555, PC645. If we map the Hamiltonians, we can similarly observe such a phenomenon using the similar method. So this work has been published in NPJ Quantum Information, and we were also invited by Nature communities to write introductions of the papers. So welcome to comment on this work. Thanks a lot.